Hello viewers, in today's class we are going to discuss an important concept in three-dimensional geometry, that is intersection of two planes, right? Although we have discussed this concept in our earlier videos, but here we are going to discuss one important problem from intersection of two planes, right? So here the problem goes like this: find the equation of the plane passing through the line of intersection of the planes. This is the first plane, this is the second plane, and here one additional condition is given, that is the plane which passes through the intersection of these two planes is parallel to x-axis, right? So let us first quickly revise the concept of intersection of two planes, right? Now suppose we have a plane like this, and let us take this plane as plane P1, and let us take another plane, say here we have the second plane, right? Now here this is plane P2. Now see, we have to find the equation of the plane which passes through the line of intersection of the planes, right? So whenever two planes intersect, here we have this plane is P1 and this plane is P2, and whenever two planes intersect in three dimensions, then they always intersect in a line, right? They always intersect in a line. So the line of intersection of planes is this, right? So this is the line of intersection of plane. Now we have to find the equation of the plane which passes through this line of intersection of these two planes, right? So it means we have to find another plane like this which passes through the intersection of these two planes, and let us call this plane as P3, right? So we have to find the equation of this plane P3. Now we know that whenever two planes intersect, right, whenever two planes intersect, then the equation of the third plane P3 is given by P1 plus lambda times P3, here we'll have P2 is equal to 0. So this is the equation of the plane which passes through the line of intersection of these two planes P1 and P2, where lambda is some scalar, or we can say it is a real number, right? So this line, when P1 and P2 intersect, they always intersect in a line. So this line is the line of intersection of these two planes P1 and P2, and from this line of intersection of these two planes we have a third plane, that is P3, whose equation is given by P1 plus lambda P2 is equal to 0, right? And here this lambda is a scalar or a real number, and the value of this lambda is to be calculated by an additional condition, and here the condition is given as this, right? Parallel to x-axis, right? So we have to find the equation of the plane passing through the line of intersection of P1 and P2 and parallel to x-axis. So this condition will be used to find out the value of lambda, right? So let us now calculate the value of lambda. Now first of all, here we have P1, which is r dot I cap plus j cap plus k cap is equal to 1, and P2 is r dot, here we have 2i cap plus 3j cap minus k cap plus 4 is equal to 0, right? Now let us first convert these two vector equations into Cartesian form, right? So this form is equivalent to x plus y plus z minus 1 is equal to 0, and this form is equivalent to 2x plus 3y minus z plus 4 is equal to 0, where vector r is any general point on the plane, right? So this is given by xi cap plus yj cap plus zk cap, right? So now p1 is given by this equation and p2 is given by this equation. Now we'll substitute this equation and this equation in equation number 1, right? So therefore p1 plus lambda p2 equal to 0 is given by x plus y plus z minus 1 plus lambda 2x plus 3y minus z plus 4 is equal to 0, right? Okay, so now here what we will do, we'll separate the coefficients of x, y and z and the constant term. So we can rewrite it as 1 plus 2 lambda x plus 1 plus 3 lambda y plus 1 minus lambda z, and here we have minus 1 and plus 4 lambda is equal to 0, right? So this is the Cartesian form of this plane P3 which passes through the line of intersection of plane P1 and P2. So once we calculate the value of lambda from this condition, we can easily find out the Cartesian and the vector form of this plane P3. Now viewers, the equation of this plane P3 is of this form, right? Ax plus by plus cz plus d is equal to 0, right? So this is the standard form of the equation of a plane, and we know that the coefficients of x, y and z, that is a, b and c, are the direction ratios of the normal to the plane, right? So now here if we take this plane P3 and suppose this is a rough diagram, and let us take the normal vector like this. So this vector is the normal vector to this plane P3, and the direction ratios of this normal vector are given by, see here, the coefficient of x is 1 plus 2 lambda, coefficient of y is 1 plus 3 lambda, and the coefficient of z is 1 minus lambda. So the value of a is 1 plus 2 lambda, the value of b is 1 plus 3 lambda, and the value of c is 1 minus lambda, right? So comparing these two equations, so the direction ratios are given by these quantities. Now here let us come to the condition which is given over here. So here this plane, that is this plane P3, is now given as parallel to x-axis, right? So this plane P3 is parallel to x-axis. So whenever we say that the plane is parallel to x-axis, it means the normal to the plane P3 is perpendicular to x-axis, right? See, let us take this plane as P3, right? This is the plane P3, and this plane P3 is parallel to the x-axis, right? This is x-axis. This is a rough diagram, and see, this plane is parallel to x-axis, and this is the normal to the plane P3, right? So when the plane is parallel to x-axis, it means the normal is perpendicular to the x-axis, right? So now we know that the direction ratios of x-axis are given by 1, 0, 0, right? And the normal vector is perpendicular to x-axis, right? And when two vectors are perpendicular, then the condition is given by a1 a2 plus b1 b2 plus c1 c2 is equal to 0, right? So when two vectors are perpendicular, then their dot product or the scalar product should be 0, and from the dot product we get this condition, that is the product of the direction ratios, and if we add all the three components we'll get 0, right? So now therefore from this condition we can find out this lambda, right? So a1, b1 and c1 are given by these quantities, and a2, b2 and c2 are given by the direction ratios of x-axis, right? So now we have these quantities as a1, b1 and c1, and a2, b2, c2 is 1, 0, 0, right? So let us substitute these values over here. So we have 1 plus 2 lambda times 1 plus 1 plus 3 lambda times 0, and then we have 1 minus lambda times 0 is equal to 0, right? So from this equation we have simply 1 plus 2 lambda is equal to 0. So 2 lambda is minus 1, so lambda is equal to minus half, right? So now we can substitute this value of lambda over here, which is the equation of the plane P3. So therefore the equation of plane P3 is given by this equation where lambda is minus half. So we have x plus y plus z minus 1, and here we have minus half, and we have 2x plus 3y minus z plus 4 is equal to 0, right? So now we can simplify it. So we have multiplying this entire equation by 2. So here we have 2 times x plus y plus z minus 1. Here we have this 2 and this 2 get cancelled, and we have minus 2x plus 3y minus z plus 4 is equal to 0, and this is 2x plus 2y plus 2z minus here we have minus 2, then we have minus 2x minus 3y plus z minus 4 is equal to 0. 2x and minus 2x get cancelled. 2y minus 3y is minus y, so 2z plus z is 3z, and minus 2 and minus 4 are minus 6, right? And if we multiply throughout by minus sign, we have y minus 3z plus 6 equal to 0, and we can also write this equation as 0x plus 1y minus 3z plus 6 is equal to 0. So this is the Cartesian equation of this plane P3, and moreover the direction ratios of this normal vector to this plane P3 are given by the coefficient of x, y and z, which are 0, 1 and minus 3, right? And if we wish to express this Cartesian equation in the vector form, we can write it as r dot, we have, see here we have no I cap component, so we have simply j cap minus 3k cap plus 6 is equal to 0. So this is the vector form of this plane P3, and this is the Cartesian form. So viewers, this is how we solve this problem in which we have intersection of two planes.